Assalamu alaikum wa rahmatullah. Our today's lesson is about balancing redox reactions. By the end of this video, you'll be able to give examples of dry redox reactions, write the corresponding redox equations of some redox reactions, define oxidation number of an element, and identify the oxidation number of some elements. The materials needed during this session are a pen and a worksheet that includes the main ideas and applications related to the video. Before we start our lesson, let's recall back some information. We said that the combustion of carbon, which is C plus O2 gives CO2, is a dry redox reaction. But the transfer of electrons is not clear in this chemical reaction. So how can we determine if this reaction is a redox reaction or not? We can do it by using the oxidation number of elements which you have taken before in grade 1. The oxidation number is an integer written usually in Roman numbers that describes the degree of oxidation of an element. It is the number of gained, lost, or shared electrons by this element when it is involved in a chemical bond. But how can we determine this number? Let's see. To assign oxidation number for an element, you have to follow the following rules. First, the oxidation number of an atom in its elemental form is 0. Example of an element in its elemental form is Fe, Cu, O2, and Cl2. Also, the oxidation number of a monoatomic ion. Monoatomic ion is an ion made up of only one atom is equal to the charge of the ion. Example, Cu2 plus, Zn2 plus, Cl minus, Al3 plus, O2 minus. The oxidation number of each one of these ions is equal to the charge of the ion. Means that the oxidation number of Cu2 plus is plus 2. The oxidation number of Zn2 plus is also plus 2, equal to its charge. The oxidation number of Cl minus is minus 1. Al3 plus is plus 3, and O2 minus is minus 2. Now, in compounds. First, the oxidation number of elements in column 1, which are alkali metals, is plus 1. An example here is NaCl and K2S. Na is an alkali metal and K is also an alkali metal. Since these elements are alkali metals and are in compounds, then the oxidation number of these elements of Na and K is plus 1. The oxidation number of elements in column 2, which are known as alkaline earth metals, is plus 2. An example is MgS and CaCl2. Both Mg and Ca are alkaline earth metals and they are found in compounds, then their oxidation number is plus 2. The oxidation number of aluminum is always plus 3 in a compound. Example, AlCl3, the oxidation number of Al in this compound is plus 3. The oxidation number of hydrogen is plus 1 when combined with non-metals, while when it is combined with metals, its oxidation number is minus 1. An examples are HCl, H2O, H3PO4, and NaH. HCl, Cl is a non-metal. Then the oxidation number of H is plus 1. H2O, oxygen, is also a non-metal. Then the oxidation number of H is plus 1. H3PO4 also, the oxidation number of H is plus 1. And in NaH, Na is a metal, then the oxidation number of hydrogen is minus 1. The oxidation number of oxygen is minus 2 except in peroxides. The peroxides which are H2O2, hydrogen peroxide, Na2O2, sodium peroxide, and K2O2, potassium peroxide, it is minus 1. Examples, H2O. The oxidation number of oxygen in H2O is minus 2. In H2SO4, the oxidation number of oxygen is minus 2. In H2O2, since it is a peroxide, then the oxidation number of oxygen is minus 1. The oxidation number of fluorine is always minus 1 in a compound. Example, Kf and MgF2. F in a compound has an oxidation number of minus 1 always. The oxidation number of each element in a compound is written per atom. For example, in hydrogen peroxide, the oxidation number of hydrogen is plus 1, whatever the subscript is. Also, the oxidation number of O is minus 1 since it is a peroxide, and whatever the subscript is, the oxidation number is not affected. The sum of oxidation numbers of all atoms in a compound is 0. It means that the sum of the oxidation number of each atom multiplied by the number of atoms of this atom is equal to 0. For example, here in H2SO4, we know that the oxidation number of hydrogen is +1. And we also know that the oxidation number of oxygen is -2. But we don't know anything about the oxidation number of sulfur, so we denote it by X. In order to determine X, we say that the sum of oxidation numbers of each atom multiplied by the number of atoms of this atom is equal to 0. Then the oxidation number of hydrogen, which is +1, multiplied by the number of hydrogen atoms, which is 2, +1 multiplied by 2, plus the oxidation number of sulfur, which is X, multiplied by the number of atoms of sulfur, which is 1, plus the oxidation number of oxygen, which is -2, multiplied by the number of oxygen atom, which is 4, must be equal to 0. We determine X, we find that X is equal to +6, thus the oxidation number of sulfur is +6. Here it's important to note that in a species, usually the oxidation number of only one element is to be calculated. Now, the sum of all the oxidation numbers of all atoms in a polyatomic ion is equal to the charge of the ion. Means that the sum of the oxidation number of each atom times the number of atoms is equal to the charge of the ion. Let's take an example here, PO4 3-. The oxidation number of oxygen is -2, while the oxidation number of P, we don't know anything about it, then we denote it by X. Then we say that the sum of the oxidation numbers of each atom times the number of atoms is equal to the charge of the ion. And the oxidation number of P, which is X, multiplied by the number of P atoms, which is 1, plus the oxidation number of oxygen, which is -2, multiplied by the number of oxygen atoms in this ion, which is 4, is equal to -3, equal to the charge of this polyatomic ion. We find X, it is +5, thus the oxidation number of phosphorus is +5. To understand this idea more, let's solve this application about assigning oxidation numbers. Assign the oxidation number of each element in the following compounds, H2C2O4 and NH4+. Solution. First, in H2C2O4, we know that the oxidation number of hydrogen is +1 and the oxidation number of oxygen is -2. But we don't know anything about the oxidation number of carbon, then we denote it by X. Let X be the oxidation number of carbon. Let's remember that the sum of oxidation number of all atoms in a compound is 0. Then 2, which is the number of hydrogen atoms, multiplied by the oxidation number of hydrogen, which is +1, plus 2, which is the number of carbon atoms, multiplied by X, which is the oxidation number of carbon, plus 4, which is the number of oxygen atoms, multiplied by -2, which is the oxidation number of oxygen, must be equal to 0 since it is a compound. We find X, we find that X is equal to +3, then the oxidation number of C is +3. For the polyatomic ion NH4+, let X be the oxidation number of nitrogen, and we know that the oxidation number of hydrogen is +1. In a polyatomic ion, the sum of oxidation numbers of all atoms in an ion is equal to the charge of the ion. And NH4+ is a polyatomic ion, then the sum of all the oxidation numbers must be equal to the charge of this ion, which is +1. Then we say that we have only one nitrogen atom multiplied by its oxidation number, which is X, plus 4 hydrogen atoms multiplied by the oxidation number of hydrogen, which is +1, equal to the charge of the ion, which is +1. We find that X is equal to -3 and the oxidation number of nitrogen is -3. The summary of this video: first, a dry redox reaction is an oxidation reduction reaction that takes place in the absence of water or any other liquid. The oxidation number is an integer written in Roman numbers that describes the degree of oxidation, loss of electrons, of an atom in a chemical compound. In a species, usually the oxidation number of only one element is to be calculated. The sum of oxidation numbers of all atoms in a compound is 0. In a polyatomic ion, the sum of oxidation numbers of all atoms in an ion is equal to the charge of the ion. This video was prepared and recorded by Mr. Mustafa Tlayas and supervised by teacher Hiba Badawi.